Picking up where we left off, we just talked about the indeterminate forms of a limit. How many were there here? 1, 2, 3, 4, 5, 6, 7, 8, 9 different indeterminate forms. Okay, if your result is one of these, here's what we'll do. Here's the rule. L'Hopital's rule is if a limit is indeterminate, if it is one of those forms, then let's take a look here. Think of this as the original problem. The limit as x approaches a, f of x over g of x. If this gives us one of those indeterminate forms, then here's what we're going to do. It's equal to, we're going to take the same limit, that stays the same, still as x approaches a, but check out what happens to the functions. We take the derivative of f of x and put it in a ratio with the derivative of g of x. Okay, what's up with that? For one, if you look closely, we're thinking of these functions independently. So f of x, we just look at the numerator only, we take its derivative. Then independently of that, we look at g of x and we take its derivative. Okay, so what's going on here? Well, if you remember, derivatives describe instantaneous rate of change. So here's my explanation. The original problem, the original limit, is the ratio of y values, right? We really want to just plug in the a, f of a over g of a, whatever a is, even if a is infinity, right? But sometimes taking a ratio of y values, doesn't get us to a definitive answer because it's infinities or, whatever, any of those indeterminate forms. We can't tell what's happening as the ratio of y values is moving towards a. So what we'll do is say, let's look at the ratio of the slopes of the tangent lines, right? The slopes of the tangent lines tell us how fast those functions are moving as we approach a. So if you think about like the tug of war, who wins, who's going faster, we want to compare the instantaneous rates of change, right? The ratios of the slopes of the tangent lines as we approach a. And that will tell us which infinity wins, or maybe, I wrote infinity here, but maybe as you're approaching 0, if that wins, that sort of thing. Now, that said, indeterminate, that said, let me back up. L'Hopital's rule is not appropriate in all limit scenarios. And we're making real clear, if the limit is indeterminate. Okay, so that leads to our last point before we get to our example. Before using L'Hopital's rule, we can't use this on anything. There's only specific times where we can use L'Hopital's rule, and we can fall back on comparing the rates of change. All right, before using the rule, first check, is your original ratio simplified? If it's not simplified, performing L'Hopital's rule could be deceiving and could very well lead you to the wrong answer. So make sure it's simplified. Number 2, well, it's like we're restating it again, but make sure that limit here gives you one of those indeterminate forms when you try to plug a in. When I say the limit is indeterminate, does it really give you one of those 9 forms we just saw? If it does, you're good to go, and you can compare the ratios of the velocities, if you will, of numerator and denominator. But if it's not, then that can lead you astray and can give you a result that's not equal to what the limit really was. Okay. Every problem we do, we are going to go through this checklist, and I'm even going to present you guys with some examples where actually, they both don't check off. Like we might see something that's not simplified or that doesn't give this, and it'll be good to mix those in, keep us on our toes. Okay, finally, here we go. Example, determine the limit. And part A is that first one I presented to you. The limit as x approaches infinity, e to the x over 2x. By the way, we've done all the theory at this point. The rest of this section is just a ton of examples. So get ready. Okay, determine the limit. X approaches infinity here. All right, well, we sort of already thought through the checklist, but let's do it again. So we're pretending like this is a new problem. Are both these things really true? So I'll say, is this really simplified? Yes, it is. Check. Right? How do I know it's simplified? There's nothing I can factor and cancel. Right? There's no conjugate. There's no common denominator to clean up, any of that. There's nothing else I can do with this. It is simplified. Is it indeterminate? Does it really give us one of those forms? Well, sure. If we plug in infinity to both, that gives us infinity over infinity, and that's in the list. So, okay, it's good to go. Right at this point, I'm going to show you what ends up being the entire problem. Let me back up a little bit here. Excuse that circle. I'll explain that in a moment. Ignore that arrow for the moment. Okay. So here I've just repeated the original limit just so we can see how it unfolds. So writing again, the limit as x approaches infinity, e to the x over 2x. Okay, and here we are applying the rule. For the moment, ignore this, what's happening here, this L apostrophe H. I'm going to come back and explain why that's needed once we're done. All right, so applying the rule. So the rule says it's the same limit, so it's still limit as x approaches infinity. But now we take derivatives. So the numerator derivative of e to the x is e to the x. And independent of that, the denominator, 2x, that derivative is 2. Okay. So we'll kind of almost like starting from the top, can we figure out what this new limit is? As x approaches infinity, e to the x over 2. So we'll attempt to plug in infinity again, and this time we're going to get an answer. Putting infinity in a second time, well, we got infinity still for the top. The limit of 2, as you guys know, any constant, it's just 2. So we think, okay, infinity divided by 2, well, that's still infinity. So we got our answer right there. And if you reflect back to the indeterminate form, think, okay, the numerator was pulling it to infinity. The denominator was pulling it to 0. Who won? Well, the answer was infinity. The numerator won. And yeah, it turns out that e to the x is approaching infinity exponentially faster than 2x. They're both headed towards infinity, but this shoots off way faster than 2x does. It runs away from 2x, and so it carries the whole thing off to infinity with it. Okay, but we needed L'Hopital's rule to prove it, to show us that without any doubt. Okay, now let me get back to this notation. So anytime you learn a new concept, there's always a new notation that comes with it. It's just the way it goes. So here's what happens with L'Hopital's rule. We need, as you can see, that's an L apostrophe H, and that's an abbreviation for L'Hopital or L'Hopital's rule. At the moment we perform L'Hopital's rule, right, from this step to this step, everyone decided, pretty soon after this rule came out, we need a way to show what we just did in our work for people to follow us. Okay, so we need to put L apostrophe H above the equal sign connecting where we performed it. Okay, so that's kind of my my note down here. So everyone can follow your thinking. You're like, what do you mean? We never do that. We always just assume people can follow our steps. If we break it down enough, then people can connect the dots and they know what we're thinking. Yes, that's normally what we do, but L'Hopital's rule is an exception. Let me show you why. I'm gonna try to awkwardly lean over and ignore that what was here. What if it was just limit x approaches infinity, e to the x over 2x equals limit x approaches infinity, e to the x over 2, and somebody was reading your work. And they were reading along and they got to this point, they're like, well, e to the x, e to the x, 2x, 2. I think they forgot the x here, and why are they just copying their work? And what happened to the x? Is that a mistake? I don't know what just happened. But if you write L apostrophe H, then they know exactly what you're. Oh, they took a derivative, and they took a derivative. I get it. So this part is key, so that everybody can follow your thinking, and that's just part of learning the rule. Now, one thing to note: we only write it at the moment we perform those derivatives. We don't write it here when we plug in, and we don't write it just at that one spot. Okay, let's do another example. Let's take a look at this. I'm going to stick to that theme of e to the x over 2x, where we're going to change up the limit. Let's say as x approaches 0 from the right. Okay, before we start going too fast and just jump right into using L'Hopital's rule, slow down. We got to go through our checklist. Is this simplified? Well, sure, of course. E to the x over 2x, we already talked about. You can't cancel anything. All right. But is it indeterminate? Okay, so when it's indeterminate, we attempt to plug in our x value, right? So plugging in 0, now 0 from the right, but plugging in 0, e to the 0 give you 1, and 2 times 0 is 0, so plugging in gives 1 over 0. Hey, is 1 over 0 in our list of indeterminate forms? No, that's not in the list. And if it's not in the list, it means we know how to get an answer to that already. We don't, not only do we not fall back to L'Hopital's rule, it would not be appropriate to go to L'Hopital's rule. L'Hopital's rule, if we performed it and did it that way, would give us a wrong answer here, actually. Okay, so then what is the answer to 1 over 0? So, think way back. That would be a vertical asymptote at x equals 0. Yeah. So we know the answer is either positive infinity or negative infinity. And we could go to a table or we could go to a graph. Here, keep in mind, it's only as x approaches 0 from the right side. So a table, we'd want values a little bit bigger than 0, or we're looking at the right side on a graph. In this case, it turns out to be positive infinity. So there you go. As x approaches 0 from the right, the values are a little bit positive, so we'll have a positive, positive. Okay, but we could get that from a table or a graph. We understand. Hey, let's pause here. These examples take some time to speak through. Let's pause here. More to come.